Hello there and welcome to the series of videos going through the content of A-Level Further Maths. Here we're going to see how we find the shortest distance between a point and a plane, so we can answer questions from exercise 9F. So the way that we're going to be finding the shortest distance between a point and a plane is by using this perpendicular vector here, n, and given that that is going to meet the plane at a right angle, it's definitely going to be the shortest direction from the plane to the point. Eventually we're going to summarize what we do in this video with a nice little formula here. So if we've got a coordinate that's A here, we've got the equation of a plane that's here, D here has been moved onto the left hand side. This here is the calculation that you have to do to find the shortest distance between a point and a plane. But let's see if we can derive this, and if you don't fancy watching this then just skip ahead about 3 minutes. Okay, so we'll say we have a point alpha, so we have a point P, and we'll call that alpha, beta, gamma coordinate. We have a point A that's on the plane, we'll call that just the coordinate x, y, z. And we have a normal perpendicular to the vector, so let's put it just straight underneath P so that it does represent the shortest distance. And this is going to create a right angle between the line and the plane. It always does, perpendicular. So what we're going to do now is create this little triangle here. It's a right angle triangle, so we can do a little bit of trigonometry on it. What we're going to do is let O be the point where the normal vector meets the plane, so we'll call that point O. Okay, so let's see if we can use some trigonometry to work out this black length distance from here to here. So onto our diagram, we're going to find the vector from X, so from P down to A, so the distance, the direction from your point down to any point on the plane. So alpha minus x, beta minus y, and gamma minus z. And what we can do is if we label theta up at the top, then the shortest distance that we're looking for is cos times by the modulus of that vector that we just created, A to P. So this is your hypotenuse, this is your adjacent line, so we want the cos of this line here. So the distance is going to be modulus of P to A times by cos theta. What we're going to do next, for a reason that you'll see for in a second, is times the top and bottom of this equation by modulus n. So just taking what we had above, times top and bottom by modulus n, and now all of a sudden what we have on the right hand side looks very similar to what we actually get in the scalar product rule. It's a modulus n, modulus AP, times by cos theta. So what we can do is use the left hand side of that scalar product rule to write that the distance is equal to n dot AP divided by modulus n. Okay, we'll carry on going for a little bit more to prove this formula down there. So that the perpendicular vector was n1, n2, n3. The direction vector from A to P was alpha minus x, beta minus y, gamma minus z, all over the modulus of n, which is n1 squared plus n2 squared plus n3 squared. Dot product this out, and this is what we get, n1 alpha plus n2 beta plus n3 gamma, all of the positive terms there, minus n1x minus n2y minus n3z. What we can do now is group some of these bits together, and what we're going to use now is something that's going to simplify what's in the bracket here, n1x plus n2y plus n3z. We're going to use the fact that the equation of the plane, if we remember to start off with, was n1x plus n2y plus n3z equaled d. So we're just going to, instead of writing all of this bit out, we're just going to use the value d that we usually have at the end of the equation of a plane. So this here is the formula. So if d is at the end after the equal sign, then it's minus d. In the formula booklet you'll see that the equation of the plane asks for it to be written like this, plus n3z plus d on the other side. So that's why in the formula booklet the formula is n1 alpha plus n2 beta plus n3 gamma plus d because d all of a sudden now has been moved over to the other side, so it's now no longer positive, no longer negative, it is now positive on the other side. Divide by modulus n. Okay, so that is the formula there. That's how we find the shortest distance between a point and a line. You don't need to know where this rule has come from. All you need to know how to do is just to apply it. So the reason we've put modulus signs around them here is just so that if the top becomes negative, we're going to make it positive, and then that shortest distance will always be positive then. So that's why the modulus symbols have gone above. For the very small subset of questions where the coordinate that we're looking for is at the origin, so in other words, our alpha, beta, gamma coordinate is equal to 0, 0, 0, then we'll have 0 plus 0 plus 0 minus d modulus, so make that positive, and it's going to be d over the modulus of your n vector. Okay, so that's a little sub-rule that you can remember if you wish to, for the shortest distance between the plane and the origin. Right, so let's have a go at these questions here then. Find the perpendicular distance from the points with coordinate 3, 2, minus 1 to the plane with the equation 2, minus 3, 1 equals 5. So just use the formula that we have been given. So 2 from here times by 3 here, plus minus 3 times 2, plus 1 times minus 1, minus this 5 value, divided by the modulus of your n vector. In this case here, your n vector is going to be 2 minus 3, 1. And just bung it into your calculator and calculate. So your final answer here is going to be the 6 over the square root of 14. Okay, so it's just as simple as substituting into a formula. Another question might be the plane pi has the equation r dot 1, 2, 2 equals 5. The point P has coordinate 1, 3, minus 2. Find the shortest distance from P to pi. As before, use the formula, plug your values in, and you get 2 over 3. Okay, it can't really be easier than just plugging your numbers into the formula. Right then, so your turn to have a go at this question here then. Pause the video and try this one out. Right then, let's have a go at this question here then. So the plane can be written as minus 2, 1, 1 equals 5. So we've clearly got an n1 value, n1 is equal to minus 2, n2 is equal to 1, and n3 is equal to 1 as well. We've got a point alpha, beta, gamma. So alpha, beta, gamma is going to be the coordinate 1, 0, 3. So now just applying our rule, the shortest distance, I won't use d because that will confuse things with the 5. The shortest distance is n1 alpha plus n2 beta plus n3 gamma minus d all over the square root of n1 squared plus n2 squared plus n3 squared. So we're going to get minus 2 times 1 in our first calculation. Then it's going to be add 1 times 0, so add 1 times 0, add 1 times 3, minus 5, all over the square root distance of 2 squared, 1 squared, 1 squared. So we're going to get on the top here in total minus 2, plus 3 is 1, minus 5 will give you minus 4. Over the square root of 6. Now we need to modulus the top to make sure it's a positive distance, so your answer is just going to be 4 over the square root of 6. Okay, so that's how we do that question there then. So it's nice and easy. You've got the formula in the formula booklet. Make sure you know where it is, and make sure you know how to use it. Thanks very much for watching.